Hi everyone, Tina here, and today I'd like to talk about variable acceleration. We'll be using calculus, so differentiation and integration, to move between displacement, velocity, and acceleration. You usually first learn about this topic during year 1 of your A-level course. I'll go through some key ideas first, and then we'll take a look at some examples. So the key idea for this topic is that if you want to move between displacement, velocity, and acceleration, you can actually use differentiation and integration. Now, because velocity is the rate of change of displacement with respect to time, that means you can differentiate to get from displacement to velocity, because rate of change is all about differentiation. Similarly, if you want to get to acceleration, which is the rate of change of velocity with respect to time, you can differentiate velocity. If you remember this order, SVA, or SVA for short, then you can remember that if you want to go down the list, then you differentiate. So DD there might be a useful trick to remember the order. Now, because integration is the opposite of differentiation, that means if you want to move up the list, you integrate. And again, you can remember that because the opposite of differentiation is integration. That is essentially all you need to know for this topic, and then it's just about applying it to different questions. Example 1. A particle P travels along a straight line through a point O, so that at time t seconds after passing through O, its displacement from O is x meters, where x is t cubed minus 15t squared plus 62t. Find the initial velocity of P. So I've got SVA in the corner there as a reminder. In this question, we're given displacement. So for part A, I would write the displacement as s equals t cubed minus 15t squared plus 62t. And we want to know the initial velocity. So v means we're going to have to differentiate s. When we do that, we get 3t squared minus 30t plus 62. And then this question specifically references the initial velocity. So that just means when t is 0. So all we need to do is sub in t is 0 into here. When you do that, you just get 62 meters per second, and that's it. For part B, it says they want the value of t for which p has 0 acceleration. So that means we want to find acceleration, which we get from differentiating velocity. That would be 6t minus 30. They want to know when p has 0 acceleration. So all we need to do is make a 0 and solve. Means 6t will be 30, so t is 5 seconds. And we're done. Example 2. A go-kart manufacturer is testing out a new model on a straight horizontal road. Starting from rest, the velocity of the go-kart is modelled by the equation, and then v equals 1/10 t brackets 36 minus t. We're told that t is always greater than or equal to 0, which makes sense because t is time. Part A says find the maximum velocity of the go-kart and the time at which this occurs. Justify that it's a maximum. Now I've got SVA in the corner there as a reminder, but you won't always need to move between S, V and A. Sometimes you just need to apply ideas of calculus to the question. So by that I mean, in this case, they're asking for the maximum velocity. That word maximum makes me think of differentiation, because if this is the graph for velocity, negative quadratic, at the maximum point, the gradient will be 0. So dv dt equals 0, and that's what we've got to work with here. So let's do that. Let's have a look at v. So 1/10 t 36 minus t. Let's expand that out so it's easier to work with. 18 over 5t minus 1/10 t squared. And then let's do dv dt, which would be 18 over 5 minus 1/5 t in this case. Now we know for the maximum that we want that equal to 0. So all we need to do is solve for t in this case. So let's do that. 1/5 t would be 18 over 5, means t is 18 seconds. We can then use that t value to find the maximum velocity. So when t is 18, v would be 1/10 and then 18 brackets 36 minus 18, which gives you 32.4 meters per second. We need to justify that this is in fact a maximum. So to do that, we need the second derivative. That's d squared v over dt squared, which in this case will just be minus 1/5. That is negative. Therefore, that's justified that it's a maximum. Part B. The go-kart does not move backwards at any point during the test. Find the time it takes to complete the test. The fact that they're telling us that the go-kart does not move backwards at any point just means that the velocity is never going to be negative. It will always have a positive velocity going in the forwards direction. That's what we need to use here. So if we say v is always going to be greater than or equal to 0, we can sub in our v equation and then just solve this as you would a normal quadratic inequality. So I would get rid of the 1/10 or divide through by 1/10, gives this. means if it was equal to 0, then t would either be 0 or 36. I would then make a sketch, really important for quadratic inequalities. So that's t and that's v. It's a negative quadratic that goes through 0 and 36. So maybe something like this. We want the velocity to always be greater than or equal to 0. So we're looking above the t-axis. And that means t is always going to be between 0 and 36. Therefore, the test takes 36 seconds. And that's it. Example 3. The acceleration a of a particle moving in a straight line at time t seconds is given by a equals 4t minus 7 for t between 0 and 6. Initially, the velocity of the particle is 3 meters per second. Find the time when the particle is instantaneously at rest. So instantaneously at rest, what that means is v will be 0 at those times. But we haven't got an expression for v velocity at the moment, we just have a. So using SVAR, that means we need to integrate a to find v. So v is going to be the integral of a with respect to time. Let's integrate 4t minus 7. That will give us 4t squared over 2 minus 7t plus c, always writing plus c for integration. Simplified, 2t squared minus 7t plus c. Now, in terms of finding that constant of integration, we are told that initially the velocity is 3. So we can say when t is 0 at the start, v is 3. Therefore, 3 equals, and then sub in 0 for time. That will tell you that then c is also 3. That means you can now write a full expression for v. So v equals 2t squared minus 7t plus 3. Now, when the particle is at rest, v is 0. So we're just going to solve this equation equal to 0. You can do that in whatever way you prefer. When you do, you should get t equals a half or t equals 3. And those are the times at which the particle is instantaneously at rest. B. Find the exact total distance traveled by the particle in the first 6 seconds of motion. Show your method clearly. Now, it's talking about total distance, but in order to work that out, we need to find the displacement first. So to find displacement using SVAR means we've got to integrate v. So let's do that. S is the integral of v with respect to time. We know what v is from the previous part of the question. So that was 2t squared minus 7t plus 3. When we integrate that, we get 2t cubed over 3 minus 7t squared over 2 plus 3t plus c again. Now, in this case, to find the constant of integration, we can assume that at the start, displacement is 0. So I'll just write that down. Assume when t equals 0, s equals 0. That would lead to c also being 0 if you subbed that in. So then we can say s is just 2t cubed over 3 minus 7t squared over 2 plus 3t, and we don't need to worry about c anymore. Now, for this question, we do need to be careful about how the particle is moving. We know from part A that the particle was at rest when t was a half and t was 3 seconds. If the particle is moving in a straight line and it's at rest at any point, it might be because it's turning and changing direction. So if we're moving along and we stop, it might be because we've changed direction. So we need to be careful just in case this has happened. So what I like to do is draw myself a little diagram. So if we're starting here at O, let's say origin, let's find out what happens between the start and when t is a half. So when t is a half, s is going to be that equation with a half subbed in. When you sub that in, you get 17 over 24 meters, which means in that time, the particle has moved, let's say to the right, 17 over 24 meters. And that's up to this point when t is a half. The next time the particle was at rest was when t was 3. So I'm going to investigate what happens to the displacement when t is 3. So if I sub 3 in now instead, I get minus 9 over 2 meters. Now that's interesting because that means in relation to the starting point O, the particle is now on the other side of it. So if I just make a mark here for where O was, it seems that the particle has moved from here back this way, past O, and then it's gone here somewhere. Minus 9 over 2 meters in relation to O, and that's when t equals 3. Finally, we're interested in the distance traveled by the particle in the first 6 seconds of motion. So let's see when t is 6, what is the displacement? So let's sub 6 in, and we get 36 meters, positive 36 meters. So it seems in that time, the particle has actually traveled quite far and has ended up all the way over here in relation to O, 36 meters away. And that's when t is 6. So if we just follow the particle through its motion, it starts here, it goes to the right, 17 over 24. It then goes back on itself to minus 9 over 2. It then goes back on itself again and much further away, this time to 36 away from O. Now we can work out the total distance travelled by just adding up all those individual pieces of the journey. So it goes 17 over 24. It then goes back on itself, so another 17 over 24. It goes 9 over 2, then back on itself to get back to the origin. And then finally, another 36. So when you add all of those up, you get the total distance, 557 over 12 meters. Easy to make mistakes on that type of question, so just take your time on that. That's it for now. If you found this video useful, please do remember to like, comment, and subscribe to my channel if you haven't already. And do share this with anyone else who you think might find it helpful. Thanks, and see you next time.